Okay, so can we then use isotopes to also say how we are burning fossil fuels? It turns out that we can. What happens there? As I said, carbon has isotopes of C13 and C12. Again, life fractionates. How? When plants want to photosynthesize, they prefer to again take the lighter isotope C12. So if you look at the photosynthesis of H2O plus CO2 forming CH2O for the carbohydrate unit, then that carbon in the organic matter is fractionated towards C12, so it is deficit in C13. What does that mean? That means when the past organic matter is burned, you are going to release more and more of C12 into the atmosphere because you're burning organic matter that is fractionated more towards C12. So if you look at current atmosphere, it has a naturally available C13 C12 ratio, but if you put large amounts of organic matter through burning fossil fuels, then you're going to put more and more preferentially C12. How does it appear? So if you look at atmospheric composition of CO2 in terms of delta C13, so it is again in terms of the comparison with the standard, same as what we did for oxygen. So you can look here at the CO2 in ppm. So we were coming out of the last ice age at 280 ppm. There a little bit of variation over much of the Holocene. Then came the Industrial Revolution. So you can see that the C13 to C12 ratio was at minus 6.5. There are reasons why reservoirs like the atmosphere or the ocean or the land remain at a certain delta C13, which we won't get into, but you can see that this is kind of the natural level here compared to the natural level of the post-glacial CO2 in the atmosphere. Industrial Revolution started with large increased burning of coal and other biomass and so on. So CO2 in the atmosphere increased, and correspondingly you can see that the delta C13 drops. Why? Because the organic matter that we are burning, whether it's coal or other forms, oil, natural gas, whatever, biomass, is depleted in C13 because it is produced via photosynthesis which fractionates towards C12. So this is a beautiful example of how we can show that increased fossil fuel burning is in fact the reason for the increase in CO2, and we can prove it by showing the changes in delta C13. There is also, of course, a change in oxygen because we are burning fairly big amounts of fossil fuel. So this is the standard Charles David Keeling's record with seasonal cycle as well as the smoothed annual CO2, showing again the increases in ppm. This record is only a short one, but doesn't matter. His son Ralph Keeling is actually collecting oxygen data and continues, I think, also the CO2 network. So you can see here there are two stations included here. You can see that the oxygen correspondingly drops by a small amount. It's called meg. It's basically molecules per million molecules of oxygen. It's a different unit. There's nothing to worry about. There's plenty of oxygen in the atmosphere, so we're not going to choke anytime soon, but pollution will kill us for sure. So this is another proof that increased consumption of fossil fuel, burning of fossil fuel, is beginning to be recorded in reduced oxygen. And again here global emissions of carbon in gigaton CO2 corresponds nicely to now the scale is reversed here, so it is going from a smaller deficit to a larger deficit to show consistency. So you can see that the atmospheric CO2 is becoming increasingly depleted in C13, relatively speaking, because we are releasing more and more CO2 from fossil fuel burning. Okay. The other carbon isotope that we use is the C14. Very quickly, C14 is formed in the atmosphere by bombarding of galactic cosmic rays, which knock out nitrogen proton, because there is so much nitrogen in the atmosphere. When nitrogen molecule is bombarded by this energetic particles, one of the protons is knocked off to convert into a neutron. So nitrogen is 7 plus 7. If you convert one of the protons to neutrons, it becomes 6 protons and 8 neutrons. So now its 6 protons is carbon. So instead of nitrogen, now you have C14 because it has 6 protons, 8 neutrons, and this is unstable. So constantly C14 is being produced in the atmosphere, and constantly it continues to decay. So if you lock it up in photosynthesis, which happens, or if you take it down into the ocean, which also happens. Remember, we said there are places where water sinks, like the North Atlantic, Greenland, Iceland, Norwegian Sea, Ross Sea, Weddell Sea in the south. That water takes out the amount of C14 in the atmosphere. As the water sinks and circulates at the bottom, it is not getting any more C14. So it begins to decay C14 along the way and becomes more and more deficit in C14. The half-life of C14 is 5,730 years. So you can go to the bottom of the ocean, sample the water masses, and see where the water masses are most deficit in C14. And you can convert that into how old that water is, or when was the last time that water saw surface. Okay, as you would expect, where the water sinks, the age converted here into a circulation age, the water is younger because it has just received C14 from the atmosphere. You can see that it begins to get older. Years increase as it circulates to the south from the region of sinking. There are regions of sinking here with younger water, but it is circulating in the Southern Ocean, as we will see later, gets older, goes into the Indian Ocean below the surface, gets older, comes back up and comes back out. So you can see some old water here in the Indian Ocean. Excuse me. Humid temperatures in Mumbai always dehydrate me. So the oldest water in the ocean is in the Pacific. We will see why that is. The water here is not sinking, so the bottom water the bottom water here is being received from the places where it is sinking. It takes a long time to reach here because it is going from the south to the, so it's sinking here, coming here, mixing here, going north, going north. This is a small ocean, so younger water, but older than here and here. This is the oldest water. You can see it's up to 1200 years old. So this is a beautiful example of how C14 is used. C14 can also be used for organic matter, old organic matter, because that also decays. But it's only 5,730 years of half-life, which means the dating, carbon dating, can only go back to about 50,000 years. You have to use other isotopes to go beyond that. Obviously, we have isotopes that allow us to go all the way back to the beginning of the Earth 4.6 billion years ago. So there are isotopes with half-life of 1 billion years, which allow us to date things way back longer than 1 billion, if we know the initial concentration and the parent isotope and the daughter isotope and so on and so forth. Okay, so let me leave that here. This is another example of how CO2 has been reconstructed from ice core. Not a big surprise. Using ice core, the bubbles that are trapped, we can estimate ice age concentrations that we came out of, how it began to increase, and how the Industrial Revolution has ramped it up higher than anywhere we have been for a long time in terms of atmospheric CO2. Okay? So again, these are very important topics, very important information, very Lots of technical details are not included here, just to explain to you how the methods work. And once you understand the basic idea of the methods, you can then be able to interpret paleo data whenever you look at it in terms of delta C13 or delta O18 or C14 and so on and so forth. Okay, so we will look at a few more examples before we close out the chapter. Okay, and we still have to explain why climate in the past changes. I mentioned mountain building, CO2 drawdown, but what happens if you go before that? Why do you have ice ages and deglacial times or interglacial times and so on? So that has to be explained as well, and we will see where that forcing comes from. Okay, see you in the next podcast.